what can we do with the theory? Well, one thing that we can do immediately is do some spectroscopy. So this will actually show us partly what kind of predictions we can make from symmetry. So there's light quarks and gluons, and they are still described, as I said, in words, but now I write on the board, by a full LQCD. Nothing changes. There was no heavy quark masses in that anyway, so nothing happens to that, at least for what we're talking about here. There could be some loop corrections, but. So if we think about MQ going to infinity, we can ask what happens to these hadrons, which I've just told you can still describe by the theory. So if you think about a Q and a light quark, which is a meson, it has the quantum numbers of the heavy quark. And remember that the number of heavy quarks is conserved in this limit. And then it has the quantum numbers of the rest of the stuff, which could be an anti-quark. It could be any number of QQ bar pairs, because we don't know how many are there. We have non-perturbative interactions. And it could have any number of gluons. And generically, we call this stuff light degrees of freedom, because that's what it is. This is heavy, this is light. And it's just a bunch of light stuff. OK, so that's kind of how we can think of the state. It's an infinite number of single particle states because it's a complicated QCD bound state. And what we want to do is we want to sort of enumerate what symmetry can tell us. Well, since we can think about total angular momentum, and that is actually a good quantum number. It was in QCD, and it remains true in HQT. The thing that's new is that the heavy quark spin is conserved. So SQ is conserved. And that we can use to say something more about the states. And usually the way that this is done is by defining SL to be J minus SQ. So if both J and SQ are good things to talk about, we can also talk about SL, which is the difference. And if you want to think of quantum numbers here, then J squared right would be, in terms of quantum numbers, some J plus 1. And so we can do the same thing with SL. It would be some SL plus 1 on a state with good quantum numbers of SL. So if we organize things in terms of SL, then we get symmetry doublets for the mesons. So let's pick an SL and some parity, make a little table. If we take a half minus, there's two mesons that fall in that camp, a B and a B star, that have little, well, let's call it capital J. Let me call it little j. J is 0 and 1 for these guys. So this is the scalar guy, and this is a vector guy. And the parity is negative, so it's a pseudoscalar. We can keep enumerating there's a guy with opposite parity. These guys turned out to be heavier. This is the lightest. Ground state heavy mesons. 3.5 plus, called B1 and B2 star. All these things have been observed. And you can keep going, and you can do the same thing for baryons. So if you do baryons, then the spin of the light degrees of freedom are not half integer, but integer. 0 plus is just the lambda b. And then the only possible j is to add half for the SQ. So what's happening is this is SL. And then remember that the Lagrangian and the dynamics is independent of SQ. So I can add and subtract at the SQ from this SL. And I get total j of 0 or 1. But the dynamics of these mesons doesn't care about the heavy quark spin. So that's why they come in a symmetry doublet. So the heavy quark spin symmetry is relating things in a doublet of given SL. That's how you should.
Notation, does star just always mean excited angular momentum, say?
Star is just another. Star is just something you can put on the B to make it not look like a B. You can put a twiddle. I mean, generically, it started out as star being the vector. Star is like kind of a notation for vectors. But then, of course, here B0 star is a scalar. So yeah. So we have the lambda b, and then here we have sigmas. So that's telling us that we're already making some predictions about mesons and baryons for that matter, just from symmetry. Now, if you want to really make predictions, you'd like to look at a little more dynamics. And for that, there's something that's kind of cool called using a covariant representation of fields. So I want to show you how that works. So we're going to see how to make heavy quark symmetry predictions by building up some object that has good transformation properties. And this is, in general, something that's a more general lesson. If you have a symmetry and you want to make some predictions that are just based on that symmetry, then you want to think about how things transform, and you can do tricks like the ones I'm going to show you. So we're going to encode heavy quark symmetry in objects with nice transformation properties. The moral of this story is that it's much easier to take traces than to think about Clebsch-Gordon coefficients. Sure.
The way you've done it so far, when you throw in this v, like, should I be worried that you've broken Lorentz invariance?
Yeah. Angular momentum is conserved. It's the boosts that are broken. But we'll talk about. We're going to come to that in a minute. Yeah, yeah. But the good question related to this discussion is the angular momentum is actually conserved. Yeah. Okay. So rather than try to make this a kind of derivation, I'm going to just tell you the answer, and then we'll talk about its properties. So I'm going to write down a field that annihilates the meson doublet for the ground state mesons. Q is the heavy quark flavor. PV mu star Q is something that annihilates a vector B star type meson. So Q could be charm as well. And PV, without the mu, is annihilating the B meson if Q is B. This is the flavor, which you can think of as, for this discussion, bottom or charm. And so this guy's a bi-spinner. It's got the indices of QQ bar, but it's turned a vector field and a pseudoscalar field into a bi-spinner. This thing here, this 1 plus v//2, is projecting out the heavy quark degrees of freedom. This is a vector, so this is like something that if you acted on a state would get replaced by the polarization. squared is -1. And v dot epsilon is 0. So that means that v dot this guy is also 0. And this is pseudoscalar. So this is the vector meson. This is the pseudoscalar. So what are the transformation properties of this? So it's a bispinner. If you do a Lorentz transformation, it transforms like a bispinner should under a Lorentz transformation. Spinor Lorentz transformation, and v prime is transformation of v, and x prime is the transformation of x. So that's how we want it to transform. We want something that is transforming like this QQ bar. We've got v slash on hv equals hv. That's one way of writing this 1 plus v slash over 2 hv is equal to hv. And that says that there's no anti-quark. So that's good. We can also, just by studying the properties of this thing, work out that hv v slash is actually minus hv. That one's not something we built in. That's an outcome. So you could work this out, though I won't go through it. You just push it through to the other side, and you can figure out that that's true. So we'll use it, but it's not something that directly was, it's an outcome of putting things together, not so much something that we built in. If we talk about heavy quark and light quark symmetries, so SQ cross SL, then it's a half under that. So if we work in the rest frame, which is this VR, which is 1, 0, then you have, if you think about doing a symmetry transformation, you get a commutator. And basically what happens is that you have two sets you have a bispinner, so you have two parts of the spinner that are corresponding to the heavy quark and two parts that are corresponding to the light quark. The heavy quark part is on the left. So, and then the light quark part is on the right. So that's the spin transformations. And this is the right spin transformation for something that's spin a half, where the sigma 4x4 is the usual spin matrix. Let me just say a bit more about heavy quark spin symmetry, which is part of our discussion there. So HV is transforming if you do a heavy quark spin symmetry transformation. It's transforming on the left. That's what I just was discussing. And if you do some transformation parameterized by some theta, which I just dot into the S over there, then this is the way you would think about what the transformation gives. So you could take this and you could plug in our HV field and then just do the Dirac algebra with the gamma and the gamma 5 and simplify this thing down and work out a transformation for delta PV and delta PV star. And what you'd find is that this guy in the rest frame here, everything in the rest frame is that, and this guy theta cross DVR star minus a half. So if you talk about the transformations under heavy quark spin symmetry of the states, these are actually getting mixed up into each other. And that's what we already were saying before when we were talking about spectroscopy, that spin symmetry was relating the two. This is us now seeing that very explicitly, that if you make a heavy quark spin symmetry transformation, the vector guy, so this guy should have a star, and the scalar guy get mixed up. And that's what spin symmetry allows you to do, is relate any statements about the B to statements about the B star. It's one thing it allows you to do. So the power of this HVR thing is that it allows us to make heavy quark spin symmetry predictions easily. Because we've encoded the symmetry in this object, kind of like our spurion analysis, we'll be able to use similar types of ideas to make spin symmetry predictions easy with this guy. So let me give you an example of that. So an example is talking about heavy quark decay constants. And we can think about B mesons or D mesons, and correspondingly B stars and D stars. So think of the Q field here that I'm writing as a full QCD field, and the P field here with momentum P, it's either a B meson or a D meson. And if just by Lorentz symmetry, much like one works out for the pion, one can write down a result that just follows from Lorentz invariance and parity for what the result for this coefficient is. I guess you also have to use time reversal. And you could also write the P as MP times V if you want to make explicit that there's some velocity that this P squared squares to the mass of that state. So this guy here is some dimension 1 constant. And if we just, in QCD, do the same thing for the other guy, which is the vector, we can do the same game. Here we have to get a polarization on the right-hand side. There has to be linear in the polarization. That's the statement about a vector. And because of parity, it's not the gamma mu, gamma 5, but the gamma mu that comes in. So we have spin 1 instead of spin 0. So there's some extra -1 from that. So we have a gamma mu here, and this is how we can parameterize the matrix element. And this guy here, if we work out the dimensions, it would be dimension 2. So just in QCD, it looks like we have these two things, FP and FP star, that are different. But we know heavy quark symmetry relates the P and the P star, so they actually should be related. So you could ask the question, how are they related? Work it out. And if I asked you that question, the way to work it out, which I'll show you, is to use this HV field. OK, so there's two things we have to work out. We're going to use the HV field. I'll show you how. We also have to think about these currents that I've talked about here and writing them in terms of the QV field. So let's do that first. So that's pretty easy. Just replace our field by the QV field. Now, if I just want to make a statement about heavy quark symmetry, then I can look at how this guy transforms under heavy quark symmetry, because I know how QV transforms under heavy quark symmetry. So just went like a D. And so what I'd like to do is I'd like to encode in a general object, much as we did in chiral perturbation theory, I'd like to encode in a general object that involves the HV field, something that has the same transformation properties as this current. Much in the same way we could think about connecting currents that transformed in a certain way to a chiral theory, we're doing the same thing with heavy quarks. So let's pretend, in order to do this, instead of thinking about covariance, we want to think about invariance. So pretend that the Dirac structure transforms such that we cancel that D. Then we have an invariant, and we can think about building invariance out of the HV field. And it's very simple, because if we think about that, gamma times HV is invariant. You only have to think about one HV field because of the number of heavy quarks is preserved. Okay, so we know there's only one. And then the other thing that transforms is gamma. And so then we can form an invariant, which is gamma H. So then, if you look at this thing, and then the sandwiching with this guy, the indices of, so this guy's got a vector index and this guy's got a scalar index, but that's all encoded in our HV field, right? It's got indices for those fields. So we're basically constructing things. If we've already accounted for the indices here on the left-hand side of the equation, then we're just constructing things that are scalars. So Lorentz covariance requires us to take a trace to get a scalar. And so we basically have trace. We can put anything we like here, and then we have gamma HV, which is like the QCD stuff, and then the heavy quark part. So we just have to write down the most general x that we can think of. And there's not that much we can do, because there's not that many vectors available to us. So there's two things that we can do. We can write down something that just is a diagonal, or something that's a v/. But then we can simplify this guy, because HV v/ is minus HV. See, I can take this, and this is a trace, so I can move it over to the other side of the trace. And if it's a v/ on the other side of the trace, then I can use this formula. And so these two guys here actually just become, after taking that into account, one thing, which I'll just call A. So there's basically a unique thing that we can write down for the x after we use all the symmetry properties of the HV. We only have one thing. And so then you can just work out what that trace is. Just take the trace, and you get A, and you get minus I v mu PV, or you get PV star mu. And this is what you get if you have gamma mu, gamma 5. And this is what you get if you have gamma mu, and if you have the other way. So for gamma mu, you don't get any pseudoscalar, and for gamma mu, gamma 5, you don't get any vector. So the way that you should think about this is that in the matrix element, and only in the matrix element, between these ground state mesons, I can really think that I've made some connection that looks like as follows, that Q gamma HV, QV is A over 2 times this trace of gamma HV if I'm in the matrix element. And then I know how to take matrix elements with these fields, because they're the fields that actually are annihilating those states. So then Q bar, gamma mu, gamma 5, capital Q. Now I'm using HQET states. That's what they're actually annihilating HQET states. And I just used the formula that I've derived over there. And I get these two results. So for HQET states, I have only one constant A. And that's because heavy quark symmetry related to decay constants. And if I look at all the dimensions of the things on this side and count them up, I find that the dimensions here are such that this should be something that's lambda QCD to the 3/2. So then I can try to go back and connect to my decay constants what this A is. And we know how to do that because I told you how to connect the states. And we talked about how to connect the currents, which is very simple. These states here are dimension minus 3/2. That's basically what leads to the different power on the right-hand side. So connect the states. That gives some extra factors of meson masses. And we find that FP is this universal constant A over square root MP. And FP star is this A times the square root of MP star. And then we're getting correctly the dimension 2 and the dimension 1 quantities in terms of one universal A. Okay? So you can make predictions from this. So for example, you could take FB, and you could say, well, how big should FB be? Well, it should be by dimensional analysis. Now that we've figured out how to do dimensional analysis, it should be of this size, and that gives you something that's not too far off. Or you could take FB over FD, and you could predict, because actually we don't care whether it's a charm quark or a B meson or a B quark. The A here didn't care about the flavor of the P and the P star state. So everything I said here could apply equally well to B states or D states. So the only place that it's coming in is when we have this explicit square root here. And if just by power counting we could say FB over FD is like MD over MB, which is about 0.6. Okay, so these are predictions that we can make based on symmetry. And then if you have a prediction based on symmetry, you could also talk about symmetry violating corrections, and people do that kind of thing to make, A is the lowest order prediction, but you could talk about violating it with some higher order A's, and those type of things are done. The real place that this gives a lot of power, I have to mention, although we'll not talk about it in detail, is when you look at semi-leptonic decays. So if you look at the semi-leptonic decay of a transition of a B meson into a D, or a B meson into a D star, then you can again use all these symmetry tricks and again use this HV field, and some of the reading will talk about these weak decays. If you were to enumerate the number of form factors you'd have in QCD, you'd have 6 form factors. And once you go over to the heavy quark limit, there's just 1. And it's actually normalized too, because it's related to a conserved charge. If you have a spin symmetry to relate it, you can use your heavy quark spin symmetry to actually relate it to the operator that counts the number of B quarks. So these form factors, you don't know anything about their normalization, and there's 6 of them. Take this limit, you get 1, and it's normalized. It's kind of nice. It's called the Isker-Wise function. Yeah.
You said that inequalities on the chart matrix elements.
Yeah.
So
why did I say that? So for example, imagine that I was to have done this for not the P and the P star, but for these other things that I was calling B0 and B1, or B1 and B2. Then when I would go through it, I would have not used the HV field. I would have had to build a field that has those guys in it, which would have spin 1 and spin 2. And that would be a different matrix element. I could still do the whole same story, But it really, this formula, this particular version of the current is only true for these states. And for other states, you'd have to use a different version. That's what I meant. Any other questions?